Hello everyone. So this is a question from JEE Mains 2026, 8th April Shift 2. The total number of aromatic compounds oblique species from the following is. Okay. So they are asking us the total number of aromatic compounds, and yeah, these are some of the compounds which are given to us, and we have to check whether they are aromatic or not. The chapters involved is hydrocarbons. Okay. So there was a guy called Huckel. So he predicted that electrons in cyclic conjugated polyenes, okay, according to Huckel, electrons in cyclic conjugated polyenes containing 4n plus 2 pi electrons, where the value of n can be 0, 1, 2, 3, etc., are completely delocalized. Okay, so here we have to understand the meaning of few words. So we know what is cyclic. We need to understand what is the meaning of conjugated, what is the meaning of polyenes, what is the meaning of delocalized. Okay, so the meaning of conjugated is, having alternate single and double bonds. Okay, conjugated means having alternate single double, such kind of arrangement of bonds. Okay, then we have to talk about polyenes. Polyenes are those hydrocarbons which contain many double bonds. That's why polyenes. Okay, and the meaning of delocalized is that electrons which are not confined to a single atom but shared among multiple atoms. That is the meaning of delocalized electrons. Okay, so delocalized electrons are electrons which are not confined to a single atom but shared among multiple atoms. Okay, so coming back to our statement, so Huckel said that electrons in cyclic conjugated polyenes, so those electrons which are present in a cyclic conjugated, having double single arrangement, and polyenes having multiple double bonds containing 4n plus 2 pi electrons. So if we have this much amount of total number of pi electrons, and these electrons are completely delocalized, that means these pi electrons are not confined to a single atom, but they are shared among multiple atoms. Okay, so because of this phenomena, because of this delocalization, these molecules become very stable, and all such compounds are called aromatic compounds, those who satisfy these observations. So they are known as aromatic compounds. Okay, and they have chemical properties which are different from other cyclic unsaturated compounds which don't contain 4n plus 2 pi electrons, and therefore the necessary and sufficient condition for a molecule to be aromatic are very important. So the necessary and sufficient condition for a molecule to be aromatic are: first, it should have a single cyclic cloud of delocalized pi electrons above and below the plane of the molecule. Very important. It should have a single cyclic cloud of delocalized pi electrons. Important. Not just any electron, pi electron above and below the plane of the molecule. So this is the first condition. And pi electrons are electrons which are present in the p orbitals. Okay, so for example, so we'll discuss this point with respect to benzene. So I will draw something. So each carbon of benzene has an unhybridized p orbital. So these are the unhybridized p orbital of each carbon. And these 6 unhybridized p orbitals have 1 electron each. So this guy has 1 electron, this p orbital has 1 electron, this guy has 1, this guy has 1, and this guy has 1, and also this guy has 1 electron each. And any 2 p orbitals on adjacent carbon atoms are close enough for a sideways overlap to form pi bonds. So let's say we are talking about this guy. So this guy can overlap with this guy to form a pi bond. This guy can also overlap with this guy to form a pi bond, right? So this participation of pi electrons in more than one bond is called delocalization of electron, and those delocalized electrons are equally attracted by all the 6 carbon atoms of the benzene ring. So this is how we show delocalization of the electrons. Okay, so therefore, to represent or to show this, I will draw a diagram. And using dots, I show that the pi electrons are, you know, delocalized. And they're equally attracted by all the 6 carbon atoms. So the pi electron here is equally attracted by all the 6 carbon atoms of the benzene ring. And therefore, we sometimes show benzene like this by a circle. So this circle on benzene represents the 6 completely delocalized pi electrons. Okay, so this is the first criteria, that is, it should have a single cyclic cloud of delocalized pi electrons above and below the plane of the molecule. So you can see this is above the plane and this is below the plane. Okay, the second criteria is it should be planar, because complete delocalization of pi electrons is possible only if the ring is planar to allow the cyclic overlap of p orbitals. So this overlap, that is, this delocalization and overlap of p orbitals is possible only if the molecule is planar. Okay, so the second criteria is it should be planar. And the third criteria is it should contain 4n plus 2 pi electrons, where the value of n can be 0, 1, 2, 3, etc. Okay, so now looking at the species or the compounds which is given to us in the question, the first one is we have this guy. So this is known as P or para benzoquinone. Okay, so important information regarding Huckel's rule is that Huckel's rule apply to cyclic systems where all of the p orbitals and electrons are contained within the ring. Very important. Apply to cyclic systems where all of the p orbitals and electrons are contained within the ring. With para-benzoquinone, we have some orbitals and electrons. That is, with this guy, we have some orbitals and electrons external to the ring. So those are not to be considered in Huckel's rule. Okay, so I'm talking about these pi electrons. Okay, so they are not to be considered when you are calculating whether it contains 4n plus 2 pi electrons or not, because they don't belong to the ring. Okay, so we can say that para-benzoquinone is conjugated, yes, because there is double, single, double, single, double, single. It is conjugated, but it is not aromatic. Okay, and also if you look at this ring, it contains 4 pi electrons and it is not delocalized over the entire ring because there is no conjugation in the ring, double, single, single. Okay, so if we do further investigation, if we draw the resonance structures of para-benzoquinone, okay, so let's try to understand. You might have this doubt. So to show the movement of electrons, so this becomes a double bond there, and this becomes a lone pair here. So we will get O with a positive charge, and in the next step, these lone pairs become a double bond here, and this pi electrons become lone pair there. So we get, and obviously this pi bond is there. So we will get O 1, 2, 3, 4, 5, 6 with a negative charge, and O with a positive charge. Okay, so when we look into detail at these structures, resonance structures of para-benzoquinone, you might think that the contributing structure 3, so this is first, second, third, so this contributing structure is indeed aromatic. This is aromatic because there is delocalization, double, single, double, single, double conjugation. It is also planar, and also there are 4n plus 2 electrons. But the issue is, since the octet of O here is not complete, it has just 2, 3, 4, 5, 6. The octet is not complete, so therefore this guy's contribution to the resonance hybrid is almost negligible. So we don't consider this resonance structure at all. So that's why this is our main focus, and this guy contains just 4 pi electrons which are not in conjugation. So therefore this is not aromatic. Okay, so therefore para-benzoquinone is not aromatic. Cool. Then the next species that we have is this guy. So we have pi bonds here and a positive charge. So the name of this guy is cycloheptatrienyl cation. Okay, cycloheptatrienyl cation. First of all, it's planar. How do I know that? Because every carbon is in this species, it is either carbon of a double bond or carbon bearing a positive charge. For example, this, all these carbons, they are part of a double bond, and this carbon has a positive charge, and both kinds of carbon are sp2 hybridized, and sp2 hybridized carbon is planar. Okay, so therefore yes, it is planar. Second, it has 6 pi electrons, so therefore it follows the 4n plus 2 pi electron scheme. Therefore it follows 4n plus 2 pi electron scheme where the value of n is 1, and these 6 pi electrons are spread over the entire ring. Again, I'm repeating, just the presence of 6 pi electrons is not enough. They should be spread or delocalized over the entire ring. Okay, so the 6 pi electrons in cycloheptatrienyl cation are spread over the entire ring. So if we draw the resonance structures, then we will understand how. Okay, so this is the guy that we start with. So what will I do? I will move these pi electrons here. So therefore, this will come here, and there will be a positive charge here, pi electrons, pi bond. Okay, to draw the next structure, what will I do? I will move these pi electrons here. So I will get positive charge here, and you can keep drawing them. So therefore you can see these pi electrons are delocalized over the entire structure, entire ring. So therefore it is aromatic. Then the next compound that we have is this guy. So the name of this guy is phenan 3. So you can see there are 3 fused benzene rings in an angular or non-linear arrangement. 1, 2, 3. So this is known as phenan 3. So first thing is it is planar. How do I know that? Because every carbon is sp2 hybridized. If you look at every carbon, it is sp2 hybridized. So it is planar. And next observation, 14 pi electrons are spread over the entire structure. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay. So 14 pi electrons spread over the entire structure. That means there is conjugation. And there is conjugation, that is alternate double, single, double, single, double, single, double, right? Resulting into delocalization of electrons. So therefore it is aromatic. Okay, so this guy is aromatic. So if you want to see, the delocalization of these electrons, I can draw few resonance structures of this guy. That is, so let's say we start with this. So in the next resonance diagram, I will move these electrons here, this guy here, and this pair there. So this will result into this, this, and this. Okay. To get the next resonance structure, what I will do is I will move these pi electrons here, this one here, this one here, this one there, and this pi electron here. So it will result into and so on, right? So this shows that these pi electrons are delocalized in the entire structure. Okay, so therefore yes, phenanthrene is also aromatic. Cool. Then the fourth compound is this guy. So the name of this guy is 1,2-dihydronaphthalene. Okay, 1,2-dihydronaphthalene. Okay, so at first sight, you can see there is no conjugation here. Double, single, single, single. So there is no conjugation. And also this particular carbon is sp3 hybridized. Therefore it won't be planar because sp3, it's not planar. There is an angle of 108 degree, 109.8, right? So, and also this guy has total of 8 pi electrons, 2, 3, 4, 5, 6, 7, 8, which does not follow the 4 n plus 2 pi electron scheme. So it might seem to be not aromatic, okay? But if we look at only this part of the molecule, right, it is planar. This part of the molecule is planar because all of them are sp2 hybridized, okay? It also has 6 pi electrons, 2, 3, 4, 5, 6. So therefore it is following the 4 n plus 2 pi electron scheme where n value is 1. And also these 6 pi electrons are spread over the entire ring because we can draw resonance structures of this kind where you shift these electrons in this fashion. So we will get a structure like this. So therefore we have planar structure, 4n plus 2 scheme being followed, and also there is conjugation over the entire ring, delocalization. So therefore, yes, it is aromatic. Okay. So the catch here is while the entire bicyclic system, that is, these two rings are fused to each other. So the entire bicyclic system isn't a single conjugated loop. Yes, because of uh, not conjugation possible here. It contains a benzene ring and molecules containing an aromatic part. It contains a benzene ring, and the molecules containing an aromatic part are considered aromatic compounds. Okay, so very important statement that while the entire bicyclic system isn't a single conjugated loop because of lack of conjugation, it does contain a benzene ring and molecules containing an aromatic part are considered aromatic compounds. Then the fifth species that we have is this guy. The name of this guy is cyclobutynyl dication. So first of all, it is planar because every carbon is either carbon of a double bond, that is these two guys, or carbon bearing a positive charge. And we know that both kinds of carbon are sp2 hybridized, and sp2 hybridized will have planar geometry. Okay. Then second is they have 2 pi electrons. So therefore it follows the 4n plus 2 pi electron scheme, in which this time n will be equal to 0, right? And these pi electrons, that is these guys, are spread over the entire ring. So if we draw the resonance structures of this guy, so it will look something like this. So what will I do is I will move them here. So it will result into draw the next one. I will move this pi electron here. So it will look something like this and so on. So can you see these pi electrons are being delocalized? Okay, so therefore it is aromatic. And the last species, the sixth one, is this guy. Okay, so first of all, it is non-planar because look at this carbon. This carbon is sp3 hybridized because it has one bond, two bond, and there are four hydrogen. So carbon bonded to four single bond has to be sp3 hybridized. So therefore, this is not on the same plane. So therefore, complete delocalization of pi electrons in the ring is then not possible, because for complete delocalization, we need the molecule to be planar. So therefore, it is not aromatic. So therefore, the aromatic species or compounds are two, second, third, fourth, and fifth. That is, yeah. So this is aromatic. This is aromatic. This guy is aromatic, and this guy is aromatic. So the total number of aromatic compound species, oblique species from the following is 1, 2, 3, 4. So the answer is 4. Okay. Thank you.